Planetary scale applications, like Amazon's shopping cart or Netflix's session management, operate under a harsh mathematical reality. At this scale, hardware degrades and network links break constantly. These are not rare emergencies, they are statistical certainties. This diagram compares a traditional database setup to a decentralized model to show why those failures matter. On the left, a traditional master replica topology relies on a central primary node. If a network link to that master breaks, writes fail, and the system experiences immediate downtime. On the right, a decentralized peer-to-peer ring architecture keeps functioning, even when individual connections drop. To keep a system continuously available, to ensure the database always accepts the next write, architects must intentionally sacrifice strict, immediate consistency. In the terminology of the CAP theorem, this means prioritizing availability and partition tolerance, creating an AP system that settles for eventual consistency. To understand exactly how this trade-off works in practice, we are going to design a decentralized peer-to-peer key-value store from scratch. We will do this by solving 3 specific engineering challenges: dataset partitioning, fault tolerance, and write latency. Surviving planetary scale traffic requires entirely abandoning the concept of a master node. We have to redesign the database architecture from the ground up to treat every single node as an absolute equal. The first problem is data distribution. This animation illustrates the failure of traditional modulo hashing. When scaling a cluster from 3 servers to 4, the mathematical modulo changes. To satisfy the new math, 75% of keys must migrate, causing massive network congestion. We decouple partitioning from server counts using consistent hashing, representing a 64-bit hash space as a circular ring with servers mapped as distinct tokens. A coordinator hashes an incoming key, finding its position, then traces clockwise to the first server, the primary replica. Because the keys map to the ring rather than to a strict server count, adding or removing a node only impacts its immediate clockwise neighbor. The rest of the ring remains untouched. Physical servers rarely have identical processing or storage limits. To account for varying hardware profiles, we assign multiple tokens, called virtual nodes, to a single physical machine. A more powerful server controls more segments of the ring, distributing the overall load proportionally. By isolating the routing logic from the physical server array, the consistent hash ring creates a topology where operators can scale the cluster infinitely without triggering a massive system-locking data reshuffle. A single copy of data on a single node is vulnerable. We ensure durability by defining a replication factor, or N, dictating the total number of physical nodes that must store copies of a given partition. This diagram shows how the system generates a preference list. The routing path continues its clockwise walk, specifically bypassing virtual nodes sharing the same physical rack. It stops only when identifying n distinct physical servers, guaranteeing data is replicated across completely separate failure domains. Without a master node coordinating these writes, replicas can briefly fall out of sync. Operators manage this using tunable consistency. By defining a read quorum, R, and a write quorum, W, they dictate the exact balance between network latency and data freshness. This logical grouping shows a replication factor of 3. If the write quorum requires 2 nodes to confirm, and the read quorum queries 2 nodes, the math forces an overlap. Because the sum of R and W is greater than N, the visual highlights the single intersecting node that participated in both operations. As long as the read and write quorums intersect, the masterless coordinator node is mathematically guaranteed to detect and return the latest written data. The network topology handles distribution, but maintaining high availability under heavy load requires the replica node to process writes in less than a single millisecond. Traditional relational storage engines fail this latency test. They rely on B trees, executing expensive random disk seeks and page splits before acknowledging a write operation. This cross-section shows the log-structured merge tree, or LSM tree. When a data mutation hits the node, it executes 2 actions simultaneously: appending data sequentially to an on-disk commit log, and inserting data into an in-memory memtable, which automatically sorts the entries. This dual write separates durability from sorting. The commit log guarantees crash recovery without random seeks, while the memtable handles complex sorting in fast RAM. As writes accumulate to capacity, The memtable locks and flushes its sorted contents to disk, creating an immutable SS table. The critical speed advantage happens before that flush occurs. The node returns a success acknowledgement the exact moment the in-memory update and commit log append finish, treating all writes as sequential appends and delaying heavy sorting to asynchronous background flushes, decouples write throughput from physical disk I/O bottlenecks. An LSM tree ensures a node never has to block or reject an incoming mutation. Even with sub-millisecond local writes, network partitions will inevitably render primary replicas unreachable exactly when a new write request arrives. Instead of failing the write, the system relaxes strict routing rules using a sloppy quorum, routing incoming data to a healthy fallback node. This fallback node accepts the write through a process called hinted handoff. It stores the data temporarily, constantly monitoring the network. The moment the primary replica comes back online, the fallback node forwards the hint and clears its temporary queue. Hinted handoff handles acute, obvious connection failures, but replicas can also suffer from silent data divergence caused by dropped packets. Fixing this requires a secondary anti-entropy repair mechanism. This visualization shows two hierarchical Merkle trees, or hash trees. The replicas compare their root hashes first. If they differ, the system traces the mismatch down the branches to isolate the single divergent leaf hash. By comparing cryptographic hashes instead of raw data, the system efficiently identifies exactly which keys need synchronization. Hinted handoff bridges the gap during temporary outages, while Merkle trees constantly scan for and cure chronic data drift. Together, they ensure the system eventually reaches a perfectly consistent state. Network partitions allow multiple users to update the exact same piece of data on isolated replicas simultaneously. The system cannot resolve these concurrent writes using standard timestamps because physical clocks across distributed servers always drift. Instead, the system uses logical clocks, specifically vector clocks or dotted version vectors, to track the causal history of the data. This graphic shows two divergent versions of a single key, each tagged with a metadata array. When a read request occurs, the system pulls both conflicting versions simultaneously. The coordinator evaluates the arrays. If one vector clock mathematically dominates the other, it proves one write happened later, safely overwriting the older version. If the clocks are concurrent, the system preserves both versions as siblings. Logical clocks prevent the database from silently overwriting or losing data during a partition. By preserving concurrent mutations, the database pushes the final conflict resolution, like merging two separate items into one shopping cart, up to the application layer. We have engineered the local storage, the routing, and the failure recovery. The final question is how these thousands of independent nodes discover each other and maintain this shared topology without a central master directory. They achieve this through epidemic gossip protocols. As shown in this visualization of the background communication layer, nodes continuously and randomly contact their peers to exchange membership lists and failure metadata. This rapidly disseminates the exact state of the network across the entire cluster. The architecture is complete. We have combined consistent hashing, LSM trees, tunable quorums, and logical clocks into a single, cohesive system. Operating at a planetary scale requires accepting an architectural trade-off. We have entirely abandoned linearizable global consistency. In exchange, the system gains infinite horizontal scaling, zero downtime, and the ability to process writes relentlessly under the harshest network conditions.